So welcome to this year's NASA Ames Summer Series. This year's series includes 18 talks. The talks vary in topics from science to science fiction, from talks that are about early beginnings of innovations to mature stages in careers. All of the talks will give you a different way of seeing both what NASA does and what the world is. It is important for us to understand that vision plays a really critical step in how we process what's around us, how we operate, and at the end of the day, how innovation starts. Today's seminar is entitled Brain Function Through the Eyes of the Beholder. It will be given by Dr. Lee Stone. Dr. Stone received his BA in biophysics in 1980 from Johns Hopkins University. He then finished an MS in engineering in 1983 from the University of California at Berkeley, followed by a PhD in 1987 in neuroscience from the University of California at San Francisco. After finishing his degree, he decided that Ames is his future for multiple reasons. So he came to Ames and did a postdoctoral fellow in the Human Factors Division at Ames under Dr. Watson, who introduced him to the art of human psychophysical measurements. And also at the same time, he fell in love with Ames. In 1990, Dr. Stone took a research position in the Life Sciences Division at Ames, where he, besides doing research, also served as a project scientist for the research project. In 1995, he transferred to the Human Systems Integration Division and established the Visuomotor Control Laboratory. Please join me in welcoming Dr. Stone.
Good afternoon, or good morning. First thing I want to say is I want to thank the Office of the Chief Scientist for inviting me to give the talk. So there's a shameless plug there. So this talk is about using eye movements to explore and characterize human brain function. In an effort to bridge the gap between psychologists who were studying visual perception and neuroscientists who were studying the eye movement neurophysiology and behavior, the Visuomotor Control Lab has developed over a period of the last 20 years a number of eye movement-based methodologies or oculometric methodologies that we've used to perform scientific research, to do human factors testing, and our latest effort in the laboratory is to apply oculometrics to establish a clinical tool that could be used to assess impaired brain function due to disease or injury. So the talk has 5 parts. I'm going to give you a quick background on the status of things 20 years ago when the Visuomotor Control Lab was established. I'm going to talk about 3 main achievements over the last 2 decades. First and foremost, the validation of oculometrics as a tool that can be used to measure visual perception and higher order brain function. Secondly, the use of oculometrics as a scientific research tool. And lastly, the recent application of oculometrics as a clinical tool, and then I'll have a few concluding remarks. So, now for the quick background of the status of things in the late 20th century. So, the conventional wisdom 20 years ago was that human visual system had 2 main pathways. Everything obviously starts with the retina in your eye. It goes to a thalamic nucleus, and then to the primary visual cortex in the back of your brain. And then from there, it split into 2 different distinct pathways. One that ended up in posterior parietal cortex, and one that, that's the dorsal pathway, and one ventral pathway that ended up in the inferior temporal cortex. And Ungerleider and Mishkin originally pointed out that most of the areas in posterior parietal cortex were involved in processing spatial relationships and motion and other things related to where things are, and the ventral pathway had neurons that were involved in identifying things and identifying objects, faces, and were involved in what they called what questions. But actually, that dichotomy morphed into a more extreme dichotomy where Goodale and Milner in the beginning of the 90s proposed a hypothesis that really dominated the field at the time, which is that the dorsal pathway was involved in controlling motor action, and the ventral pathway was involved in visual perception, and that these two pathways were distinct. Now, that tidy dichotomy there, neglected a number of things. There was a low-level brainstem pathway that evolutionarily existed in reptiles and all the way up, but it's involved in controlling eye movements. And in primates, that subcortical pathway also connects up with the cortex in an indirect pathway, and also highest order visual processing and cognitive processing of the frontal cortex feeds back both to brainstem areas, brainstem areas and parietal cortex. And so the reason for showing you this slide is to show you that the story really isn't that tidy. And indeed, even 20 years ago, Van Essen's lab and others basically had pointed out that when you go from the retina, there may be a ventral path and a dorsal path, but the fact is prefrontal cortex and all these areas all interconnect in a very complicated network. And so there really is no clean dichotomy between the dorsal and ventral pathways for action and perception. Well, simultaneously with those efforts in visual perception and neuroscience, there was an almost separate field of oculomotor behavior and physiology. That basically was dominated and started by David A. Robinson at Hopkins. And he pushed forward an exciting new quantitative, computational way of looking at eye movements based on linear system theory. So this slide shows a typical eye movement that would occur in response to a sinusoidally moving target. So you follow that target as it moves back and forth. And what you can see is there are these smooth components, but every so often when you get behind the target, you have these quick jumps to catch up because you're behind the target, you want to catch up. Now, if you look at that as a plot of eye velocity over time, what you see is a nice smooth sinusoidal oscillation in eye movements with these interspersed jumps, these pulses of rapid eye movements. And so humans have two voluntary systems for tracking moving targets. You use this smooth component, or called pursuit, which generates the smooth main component of the response. And then there's also these catch-up saccades. And what David A. Robinson and his progeny in eye movement research developed were these simple control systems that work to drive the retinal error image to 0. So if you're tracking something, it has an image on the back of your eye. If you move your eye such that you get that image to stop moving, then you can actually track the target. And so you have a simple negative feedback loop, and it's independent of any higher order visual processing, consistent with the dichotomy of Goodale and Milner. Now, that view culminated in some very elaborate and quantitative models at the end of the 80s, where all of these models were based on retinal image motion being controlled by pursuit. And they all start off with a retinal error. Whoops, these buttons are too close. Bad human factors. So there's this retinal image motion, which is the difference between what your eyes are doing and your target. And with a delay, it goes up into visual cortex. And with with a few static nonlinearities and a bunch of linear processing, drives a simple negative feedback loop. So the second component is there's a negative feedback loop that you can drive the error to 0. And then in order to keep the eye moving, when you've reached that steady state where there's no more error, you have a velocity memory pathway that you use to sustain eye movement when there's no more error. So once again, all these models, pursuit is driven by a simple retinal image motion control loop with two main components, negative feedback and an internal memory. So that was the dominant view of the field when I got my PhD and came to Ames. But there were always some troubling little details out there in the world where, you know, folks just tended to not pay attention to it, but they were very important little pieces of information. I think I have to do this, and it will work. So imagine a rolling wagon wheel with 4 red dots on it, and each one of those red dots is moving along a nice cycloidal path like that. And so when you have all 4 of them moving together, you know, you see a rolling wagon wheel, but all of the motion there is actually cycloidal. So there's no image motion that's purely horizontal. But when you look at this and you track this, you see a rolling wheel, and you generate smooth pursuit horizontally. And so what, whoops, okay, it runs again, but good. What Steinbach concluded is that pursuit is a complex control system that works to match eye motion with an internal brain representation of perceived object motion. So it's something much more complicated than simply driving retinal motion to 0. However, the linear system theory folks pointed out there's a flaw in this experiment. If you blur this, you know, you can generate a blurry thing that moves rightwards. And so maybe you don't have anything complicated. You just have a low-pass linear filter of some kinds that blurs the dots, and so you see this blur moving to the right, and that's what you're tracking. And so because of that flaw in the experiment, folks basically dismissed this. And so that was the state of affairs. So when I got here, there were 2 dominant theories. The neuroscience theory of, you know, Goodale and Milner, that visual processing for perception and motor action were distinct and separate. And there was this whole oculomotor crowd that had models of eye movements based on retinal image motion, simple negative feedback, devoid of any reference to higher order visual processing or perception. So in order to bridge that gap, the Visuomotor Control Lab focused on actually measuring visual perception and eye movements as well. And in particular, what we wanted to do is to measure them simultaneously so we could make comparisons about what the eyes were doing and what perception was doing. And what we really wanted to do in order to develop oculometrics as a faithful measure of visual perception is we needed to have quantitative measures from the eye movements, but we wanted to be sure that they were actually measures of higher order brain function related to visual perception and not some other visual system, the way that Goodale and Milner had proposed. In order to validate a new way of doing things, you have to look at the state of the art of the old way of doing things. And so psychophysics is the state of the art on how you measure. It's the gold standard of how you measure perception. And what you typically do is you have subjects sit in front of a screen, they fixate, then at some point later, a stimulus comes up, or maybe 2, and then a little while longer, you know, it shows for a couple of seconds maybe, and then at the end you have to do a button press. The visual stimulus, you know, it could be a target motion, but the motion is typically constant within a single trial, but you can vary the direction or vary the speed or vary some other parameter slightly trial by trial. And at the end, what you do is you give a single binary answer. You say the first one was faster than the second one, or you say that the target moves to the left of straight down or move to the right of straight down. So you make a single binary answer at the end of the trial, and you record that. I think this will work. There we go. So the point to make here is that a single bit of information from the button press is recorded for every 1 to 3 second trial, and that's not a very efficient way of collecting information. So the way it works in a little bit more detail is you know, you have a target, it moves down, you have to answer left or right. Okay, that one's clearly to the right, and that one's clearly to the left, and this one's a little bit harder to tell, but I'm going to say right. You know, this one's harder to tell, I'm going to say left. And what you can do is you collate all of those answers, those single-bit answers, into a graph where you plot the probability of, let's say, saying rightward as a function of the direction of the stimulus. And when the stimulus is moving very far to the left, you always say left, so you never say right. And when it's moving very far to the right, you always say right 100% of the time. And in between, you know, there's this transition, this smooth sigmoidal transmission, transition from leftward answers to rightward answers. And from that curve is called a psychometric curve. You can generate two quantitative measurements. The first is called bias. You look at the 50% point, the point of equality there, and that tells you where you're equally likely to say left and right, or that's where you think straight down is. And so you measure that, and you look at, in this particular case, straight down is, you know, 1 degree to the left. And so what this means is you have to move the target 1 degree to the left in order to see it as going straight down, because you have a 1 degree rightward bias. The second bit of information that you can gather from a psychometric curve is the precision, or the slope of the curve. Now, if you're really good at the task and you have high precision, then you're going to say leftward until it's really very close to straight down, and then you're immediately going to say rightward on the other side. And so there's a very steep slope indicating very high precision. Whereas, you know, if the task is very, very hard, the object is hard to see, there may be a wider range over which you have uncertainty. And so that gradual slope, or the lower slope, indicates a lower precision. Now, so what psychophysics really is, it's a mathematically rigorous method for measuring biases, which are systematic errors, by looking at the offset of the psychometric curve, and also measuring precision, which are measures of random error, and that is indicated by the slope of the psychometric curve. Now, the downside is that this is an inefficient methodology in that it typically takes hours to collect a full set of data for every observer. And it's also somewhat obtrusive because it's hard to embed that task into a relevant applied task. So those are some of the motivating reasons for trying to find a different methodology. Now, as I said, the first thing we had to do is to validate oculometrics, and I'm going to show you 4 sets of experiments by which we did simultaneous psychophysics and oculometrics. We measured the data both ways, and we compared them to show that really it is giving you the same answer. And so the first thing I'm going to talk about is about precision of motion signals, direction, and speed. And the first thing we had to do is, you know, you have this eye movement response. It's got a whole lot of data there, but you want to compare it to psychophysics, which is a single binary button press. So what we did is we converted the eye movement trace into a single answer. So you take the average direction of the trace, and there's your answer. If the average direction is left, you say left. If the average direction is right, you say right. And you can therefore convert all of the eye movement data into single binary decisions and plot them the same way you'd plot a psychometric curve. Now, when you do this for a direction discrimination task, this is what you get. What you see is the oculometric curve and the psychometric curve superimposed. These were collected at the same time from the same observer. And so as I said, the first thing you have to do is you have to convert the binary pursuit decisions to build an oculometric curve. And then secondly, you can compare the two curves. And what you see is that they indicate that direction discrimination has the same precision for eye movements and perception. They have the same signal-to-noise ratio, which is that ability to resolve small differences in direction. More interestingly is if you measure this for cardinal directions, up, down, left, right, which is what I showed before. Once again, this new experiment, you know, confirmed that the psychometric and the oculometric curves superimpose. But we also looked at the obliques, and what you see there is they superimpose again, but they're much shallower. And that's because both the psychometric and oculometric curves indicate the same lower precision for oblique motion, which is what they call the oblique effect. Both eye movements and perception have an oblique effect, and an oblique effect of the same size. So what about speed perception? And in basically the earliest paper with oculometrics in it. Eileen Keller and Suzanne McKee at Smith Kettlewell in San Francisco, they did a study in the late 80s where they looked at speed discrimination, and they looked at eye movements and perception simultaneously. They calculated the precision of the speed perception. They plotted the inverse of it, and what they showed is, pursue or perceive, basically the psychometric and the oculometric functions have the same precision. But more importantly, in addition to the fact that it confirms that they have the same precision, it has the same speed tuning in that as the targets move slower and slower and slower, it's harder to determine their speed, and the precision goes down, or the inverse precision goes up, and both of them show exactly that same tuning below 1 degree per second. So as far as precision goes, it matches. So if you do the oculometric task, and you calculate the oculometric function, you're going to be able to collect the same information you would have had you used psychophysics. But one of the problems with this is, well, okay, so they show the same amount of noise. But that doesn't show that it's the same noise. Maybe they're equally sized noise, but it's still different systems. And so the logic that you could bring up is, well, what if you have a system where there's separate but equal processing? So you have a stimulus, different set of neurons are calculating direction for perception, a different set of neurons are calculating it for the eye movement. They have the same amount of noise, but the noise is different, versus a situation where they're shared, a pool of neurons is calculating direction for both perception and pursuit, and they actually have not only the same size noise, they have the same noise. How can you distinguish between these two? Well, the trick that Rich Clausis and I decided to use, Rich is went to the Salk and is returned to NIH, was what if we look at trials where there's no correct answer? If you look at the straight down trials, the ones where your left-right answers are random, well, if you have different noise, then your eye movement guesses and your perceptual guesses will be the same randomly 50% of the time. Whereas if your guesses are correlated, are the same, then it's because you're actually looking at the same set of neurons. And so we did that, and what we found is, lo and behold, if you look at the directions where there's no correct answer, that you typically find between 70 and 80% correlation in the answers. It's significantly higher than chance. So you must be looking at the same noise when you're guessing to try to figure out what to give an answer when you have no signal. And the reason why these aren't actually completely correlated at 100% is that there are independent noise sources. The eye movement has eye tracker noise in it that the perceptual response doesn't. And the perceptual response has button press noise in it that the eye movement doesn't have. And so that's why they're not fully correlated. But they are correlated significantly above chance. And so what we can conclude is that these random trial-by-trial fluctuations when there's no signal covary, even when there's no correct answer. And so at least some of the neurons encoding direction are shared between these two systems. And that clean dichotomy cannot explain these results. Now, another way of looking at validating whether or not visual perception and eye movements are driven by the same motion signals is to look at illusions. Illusions are when the brain gets it wrong. Your brain is a very powerful processor, but sometimes it just gets the wrong answer. And when it does, well, do the eye movements get the wrong answer, the same wrong answer, or do they get a different answer? Well, in order to do that, we looked at a visual illusion, and this particular illusion was discovered by Brent Buter and, let me move this out of the way, and Mulligan and myself in the lab back in the early 90s. And what do you think? Do you think this thing's moving to the right or the left of straight down? Somebody. What? It's rotating. That's interesting. I apologize for the jumpy video because this is PowerPoint and VGA, but basically, typically subjects see this moving slightly to the right of straight down. Is that what people are basically saying? Hopefully. Okay. So what the paper showed is that if you tilt the aperture that you're looking at a pattern moving in, that you see a bias in the direction of the long axis of the window. And so what happens with eye movements? Well, we did simultaneous psychophysics and oculometrics, and we had 3 conditions: a tilted right, tilted left, and a circularly symmetric window. In the symmetric window, these are the psychometric curves. There was no bias. Straight down was straight down. But when you tilt them, you get a systematic bias of about 10 degrees, just as you'd expect from the original study of the illusion. But if you look at eye movements, you get the same thing. You get a same shifting of the curve where they have the same biases as the psychometric curves. So once again, what this shows is when the brain gets it wrong, the eye movements get it wrong as well as visual perception. So once again, they indicate the same bias or errors. So last but not least, I've shown you when there's no signal. I've shown you when you get it wrong. What happens actually when there's 2 correct answers? And that's another way of looking at this. And in order to look at this, Jean Laurenceau and Maggie Shafrar discovered a very interesting phenomenon in the early 90s where they showed that context dramatically changes your visual perception. And in particular, they used this occluded diamond stimulus, and what they showed was, if you show, the pieces of that diamond, on a blank background where there's no context whatsoever, what you see is 4 moving segments just bopping up and down, getting closer together, further apart, and moving up and down. Is that what people see, vertical motion? Okay. Now, and this is what happens when you make 2 parts of the background, or you make 2 parts of the foreground turn into background by making them dark. Then what you see is a diamond moving up and to the left, down to the right, up and to the left, down to the right, up and to the left. Does everybody see that? Yes? No? Maybe? Okay. So the point here is the motion in this stimulus is identical. Nothing changed except for the context. Now it looks like you're looking at this thing through 2 windows, and it's blocked so you can't see it all. And so you see it moving back and forth between the 2 windows. And it's moving diagonally here, whereas before, the exact same stimulus, because there's no obvious window there, you don't know what to make of it, and you turn it into 4 separate pieces. So this is different perception despite identical image motion. And this is what happens when you look at the eye movements. If you give them the incoherent segment motion stimulus and you move the diamond diagonally to the left or to the right, you always get vertical pursuit eye movements in both those conditions. Perception and pursuit both see vertical segment motion. And when you give them the coherent diamond, lo and behold, when they go plus and minus 10 degrees diagonally, you get plus and minus almost 10 degrees diagonally there in the eye movement. Perception and pursuit both see the diagonal object motion, just like, so they're sharing that interpretation of the stimulus. So, in summary, on the validation studies, eye movements and visual perceptions are linked because they share the same precision in the direction and speed signals. They share trial-by-trial guessing when there is no correct answer. They have the same vulnerability to illusions, at least the ones I showed you. There are more that I could have shown, but due to time, I only could show you 1. And they also share the same interpretation when there are 2 correct answers. And so you can conclude that eye movements, therefore, can be used as an indirect window into these higher-order brain processing, with oculometric technologies now being able to provide a faithful quantitative measure of dynamic visual motion perception, visual motion perception. So, can we use these methods to do some science? And I'm going to show you 4 different experiments to hopefully persuade you that it can be a useful tool. The first one is, remember, we're looking at eye movements, so we're not only getting information about vision, we can say something about motor systems. And so there is an impact on visuomotor control modeling. And so before I was emphasizing that validation studies were sort of an engineering study to validate a new technique. Now I can tell you what the scientific value is of those validation studies. And in particular, the occluded diamond experiment shows that identical image motion is pursued differently when the object trajectory is perceived differently. And so what that data those data show is that it rules out these image motion models of visual motor control. What it is actually, when you think about it, it's the Steinbach experiment. But this time, it's more cleverly designed so that the linear system folks can't say, just filter it, just blur it. There is nothing you can do with a linear filter to change the incoherent diamond stimulus into the coherent diamond stimulus. There is no motion energy diagonally. You have to infer the diagonal motion using higher order cognition because the raw motion is purely vertical. The centroid does not move diagonally. And so it's basically the Steinbach experiment over again, but this time there is no way to get around it. And so it suggests a new family of models worthy of further exploration with a new role for cortex in the cerebellum in visual motor control. And so this is the old retinal image model that I talked about. You have a sensor signal, negative feedback. Visual cortex is just basically processing that sensor signal. And then the brainstem is merely providing eye movement memory. That is the retinal image motion model. All of them basically have this in common. And it's basically a robotic model. And this is why I thought it was important to point this out to folks here, is that you can try to do robotics by having simple sensors drive motor outputs directly without any higher order processing. But you have to make a different loop for every single system you're trying to control. And then you have to make sure that the loops work together. And so a smarter way of doing this that's consistent with the data that I've shown you, but obviously there's a lot more to be proven, is that the visual processing in the cerebral cortex computes object trajectory, something much more complicated than simple motion on your retina. It segments the image into different objects. It integrates them back together again so that you put the diamond together and you know what belongs with it. You also use higher order expectation and knowledge and prediction to see these things. And also there has to be some kind of a coordinate transformation, because if all your information is in sensor coordinates, but all of your actions are in the world, you have to somehow transfer your coordinate system from the sensor coordinates to world coordinates. And so there's a much more elaborate problem going on here being solved by the cortex. And indeed, that is probably why there's this massive evolution of the visual cortex and visual processing areas in primates, because it's doing this very complicated task. And the reason why that has such a value evolutionarily is once you have perceived object motion, then you can use that to drive all your motor systems. You have one good or your best solution to do that. And then the brainstem's job at that point is to just filter the commands so that they match the motor dynamics of the thing they're controlling. So you basically have a pre-filter here, and here you can have linear filters that are tuned to the output device. So if you're driving an eyeball, you filter it some way. If you're driving an arm, you filter it a different way. If you're driving a car, you filter it a different way. And the bottom line is you can use that for motor learning as well. So this is a brand new way of thinking about how the brain works for visual motor control, and it has useful applications for roboticists as well. So second scientific study, the oblique effect. Well, I told you already that there's a directional variation in the precision. The signal-to-noise ratio varies as a function of direction for both perception and eye movements. But is that due to some variation in the signal or variation in the noise? Now, if the signal is varying, then what you're going to see in plots of pursued or perceived direction as a function of target direction, you're going to see a wiggly line. And then the fatness of that line is the noise, and it stays the same, but the signal wiggles. Whereas if the noise is what varies, you'll have a nice straight line between target direction and perceived direction, but you'll have bulges here where you have high noise in the obliques and low noise along the cardinals. So which one is the case? Well, because oculometrics isn't giving you a binary answer, and we can actually plot pursued direction as a function of stimulus direction, this is what we get. A fat, wiggly line. And so the first thing we can conclude is that the signal is varying. And I can tell you that was a surprise. Because what that's telling you is that small changes in direction are magnified near the cardinal axes. You're blowing everything up. And then near the oblique axis, you're shrinking everything down. So you're distorting the world while keeping the noise actually the same. And so if you plot that magnification, what you see is, these high magnification and the cardinal directions, low minifying in the oblique directions. And one of the things to remember is evolution is not driving fidelity in your visual system, it's driving utility. And for some reason, it's really useful to magnify the cardinals and to minify the obliques. There's a lot of theories about why, but it's telling us something. We evolved to do this because it's useful somehow. And once again, this is characterized by actually two parameters. One is this fourfold anisotropy, which is the cloverleaf. And there's also, and we gave an extreme version here so you could see this, is there's also sometimes a horizontal vertical asymmetry as well, where it's taller than it is wide or wider than it is tall. Okay? So that comes from the fact that oculometrics is giving you a lot more information than a binary answer. What else? Well, binary answers, the button press only tells you something about what's happening at that instant in time when you hit the button. And oculometrics actually gives you a time course. So if you want to look at coordinate transformations, well, if your head's upright, the world is upright, your head's upright, your eyes are upright. Basically, all these coordinate systems are the same, and so it's sort of hard to distinguish. But if you tilt your head to the right or to the left, your eye counter-rolls back the other direction, but doesn't do it completely. And so when you tilt your head, let's say 18 degrees, 18 degrees, your eyes are 14 degrees tilted, and the world is not tilted at all, so you can actually separate those. So then what we can do is we can look at this coordinate frame change over time. So this is the cloverleaf pattern immediately as you begin to move your eyes. And what you can see is it's aligned with the tilted eye. It's not in head coordinates, it's not in world coordinates, it's in eye coordinates. And let's see what happens over the next half second. What you can see is actually the oblique effect, a cloverleaf, starts to fade. It's fading, but as it fades, it also rotates towards the world coordinates. And so you can watch that over time because you have data at a wide number of time points when you collect the eye movement data. So, So the anisotropy rotates over that 400 millisecond period from eye coordinates to world coordinates. Lastly, as far as science, what about predicting the effects of spaceflight? When you're launching on the top of a rocket like SLS, you get to elevated G levels. And you're lying on your back, you have 1 G on Earth, but good. We have a wonderful device here at Ames called the 20G centrifuge, where you can bring people up to 3.8 Gs, and you can actually simulate the G conditions that are very similar to the ones that you would have when you're launching a rocket. And so the question we have is, well, does vision change when you're at G? And this shows the cloverleaf measured at 1 G and measured at 3.8 G. And what you can see is that while the cloverleaf doesn't go away, it's kind of squashed. And so increasing G loading, similar to the launch conditions, causes a vertical squashing of the cloverleaf gain. And actually, if you plot for all of the 6 observers we ran in this, what you can see is that while the anisotropy bounced around a little bit, it was just as often higher and lower. This is plot of the anisotropy and the asymmetry at 3.8 G versus 1 G, and the dashed line shows you when they're equal. And so it's just as likely to be higher as lower, and the error bars show you that they're not really significantly different. Whereas if you look at the asymmetry, all 6 observers show a lower asymmetry, and actually some of these observers are actually individually significantly different than that line. So what we could say is that while there's no systematic change in the cloverleaf anisotropy, there is a consistent reduction in the vertical asymmetry of their perception. So, lastly, we want to, in our latest effort, see whether or not we can use oculometrics as a tool to measure impairment in visual function. In order to do that, we had to devise a very compact and simple test. Okay, good. Nope, that did not work, sorry. Maybe this works. Yes. So we test all possible directions of motion in 2-degree jumps, 2-degree steps, and we measure a range of different speeds, and we could collect 180 trials in order to look at motion perception. And so this is our compact version of our oculometric testing. And each 1-second trial theoretically yields up to 12 bits of information for every 4 milliseconds, because we get a separate sample every 4 milliseconds. So this shows you how much more information potentially is in the eye movement traces. But the most important thing is that in a 12-minute to 15-minute session, we can get a full set of data for the observer, yielding 10 different measures, 2 for response initiation, 3 for steady state tracking, 3 for direction tuning, and 2 for speed tuning. This shows you a typical summary chart from a normal, healthy individual. We measured this in 40 people, and what you can see is these two show you a reaction time of about 170 milliseconds, an initial vigorous response of 150 degrees per second. These 3 tell you something about steady state tracking, and these 2, this one is familiar to you. This is showing you the direction tuning and properties, and this is showing you speed processing. You get all of that in 12 minutes. And so this shows you what a normal person looks like, but what happens if you have neural pathology? So this shows you what a retinitis pigmentosa patient look like. And what you can see, and I'm going to see if this animates well. Yeah, it does, kind of. What you can see is if you look at the initiation, there's a dramatic increase in the latency and a dramatic decrease in the initial acceleration, which is what you'd expect from someone whose peripheral retina is not working very well. And you also see a dramatic, here we go, a dramatic decrease in motion processing, where both direction tuning and speed tuning are severely compromised. Now, I want to emphasize, this person's driving a car, walking around, and in all other respects is basically okay. And we're seeing these dramatic differences. And if you compare this person's performance to our normal distribution, all 10 parameters are decremented. So the chance of that is about 1 in 1,000. And if you do very conservative statistics on this, you basically can show that 5 parameters are significantly deviated from normal in this patient, and yet they're basically okay. So this shows you it's very sensitive, and these deviations are like up to 4 standard deviations away from normal. So this is a very sensitive measure. Now, hopefully this will work. Yes. We can't show you all 10 dimensions at the same time, but we can show you 3. So this is 3 dimensions of the 10 measures that we're looking at. And this is the population of normal patients, normal population. And that red dot that just came on is the RP patient. And what you can see is that he's an outlier in a particular direction. But then what we did is we waited 18 months and measured again. And there he is. And what you can see is along a very similar axis, he continued to have the performance degrade. And so we were able to watch that impairment increase over time due to the degenerative pathology of his retina. In order to boil that down into a single parameter, what we can do is you project the point onto that RP vector, the direction of the impairment, and you get a single scalar dot product which tells you what we call the RP impairment index. It's a single scalar that tells you how impaired is the person along that RP direction. And when you show that for this patient, this is the impairment of the normal population is on average 0, and what you can see is in 2013 there was a 2 standard deviation impairment, and there's a 4 standard deviation impairment at this point in time. And so oculometrics allows us to monitor impairment changes over time, which will either allow you to see degeneration or recovery from an illness, or to allow you to estimate the value of a therapeutic intervention. If you do something, is the person getting better? Well, you can measure whether they're getting better. So this is the normal person again, but what I want to do is compare this to a different pathology, which is traumatic brain injury. We looked at 31 patients who had a brain injury at some point in the past. We're not looking at them acutely, and it varied from mild to moderate. And we started to look at that population to see what we could see. And what you see here is this is an individual brain injury patient, even after recovery. And what you can see is that there is, once again, a very dramatic impairment to motion processing. If you compare this person's measurements to a normal population, all but one parameter is actually decremented, which is 1 chance in 100 just from coin flipping. But if you do rigorous and conservative statistics, at least 2 of these parameters are dramatically reduced, and this one by 4 sigma. So lastly, as I showed you before, if you look at the 3 particular dimensions, this is the normal population along those 3 dimensions, and the red dots there show you what the population of TBI patients look like. And once again, whoops, why isn't it? So what I want to just say again is, while I have the time actually, if you notice this outlier here, we were concerned about this person in our normal population, and we went back to the IRB and asked them what we should do, and we ended up notifying them that we have some concerns that they should follow up on because they stick out there as well. But what you see is this population of TBI patients, many of whom have recovered, and they have a particular direction of their deficit, all pointing generally in that direction. And once again, we can project onto that direction to get a single scalar value, and this shows you the TBI impairment index for the entire population. And what you see is that the population is shifted by almost 2 standard deviations to the right, which shows you that on average they have a significant impairment, even though they've recovered over quite a distinct period of time. But we were very interested in actually looking at whether, these guys look pretty normal and these guys are pretty seriously impaired. What's going on with that? And what we did is we asked each individual what their self-assessed residual impairment was on a scale from 1 to 10, where 1 is I have little or no residual impairment, and 10 is I'm completely impaired, I'm basically comatose. And we wanted to divide up this population into those different groups. And this is what it looks like when you do. Well, if you look at the people in group 1, the people who said they have little or no residual problem, they're almost not detectable. There's that 60% detectability here, which isn't significantly different than chance. But all of the other groups basically have a 90% detectability. So what this shows is we have a very sensitive measure for people who have mild to moderate TBI. They have recovered, and yet these are not acute patients, but the ones who say, I still have a problem, we're able to detect that with a 90% reliability. Now, this self-reported severity is not a gold standard, and so what this shows is that we've begun the validation process. What we need to do next is a real clinical study where we compare our measurements with the standard care that would be given by a neurologist. So with that said, I want to conclude that what oculometric technologies provide is a powerful neuroscience tool for basic research. Basic fat thumb, and I'm not even big. A powerful neuroscience tool for basic scientific research that we've used to explore higher order visual function of the human brain, a validated human factors tool for applied research to quantify human performance limits in aerospace conditions. And what we're working on now is to generate a sensitive clinical tool, to validate a sensitive clinical tool for detecting and characterizing mild impairments of brain function due to injury and disease. We hope to apply that both to NASA's problem related to astronauts who have visual problems when they are in space for long periods of time, but we also could apply this to mild concussions in sports and or in the military. So that's the end of the talk. I just want to thank NASA for funding and nurturing this low TRL work for several decades so that it could come to this higher TRL fruition while also enabling some science on the way. And I also want to thank the people who did the work. Dorian Liston, who's in here somewhere. Dorian? somewhere. There he is on the side. Dorian is a person who is in charge of all of the clinical study that we're doing in order to apply oculometrics to clinical assessments. Brent Buter was in the lab 20 years ago and and he's probably in the audience here too as well. Brent? Anyway, Brent was at the birth of oculometrics and did some of the initial studies of validating oculometrics. Anton Krukowski was here about 10 years ago as a postdoc and initiated all of the work related to the oblique effect. We have two San Jose State students in the lab. Lily Wong basically collected all of the data and analyzed all the data for the clinical study that you saw. Angie Godinez worked on the centrifuge study and is actually headed off to a PhD program at Berkeley in neuroscience, so we're very proud of her. I mentioned Rich. Rich and I go way back. We were graduate students together, but he and I, at the very beginning of this, went to NIH to use their invasive iCoil eye tracker because our eye trackers here had too much noise. And so some of the initial studies before we could improve the eye tracker technology were done at NIH with that invasive tracker. And then lastly, Jean de Ranceau did a year visiting the lab and brought his wonderful occluded diamond stimulus with him, which enabled us to actually make some major progress. So thank you very much.
We have time for a few quick questions. Please file through the center aisle and find the microphone in the front.
Yes, very nice. I have a question about your model of the pursuit system. You have a direct link from V1 to the parietal zones of MST and MSTD. But the experiment suggests that the pursuit system actually uses the whole object as a target. So my question then is, where in your model would you fit the segmentation of the image? And wouldn't you agree that additional parts of the ventral pathway need to be included in the model, including the higher areas of V2, V3, and V4? Obviously,
I'm trying to find the model so we can actually talk about it, but I think it's later. It's not that one, but it is, okay. Obviously, both the chart through the cortex is a bit of a cartoon in that all of those areas are involved. Here we go, bingo. The chart basically neglected a whole bunch of areas, but in this lump here, there's a lot of information about what MT does, what MST does, what the frontal eye fields do. And you're actually correct if your question was that obviously there needs to be more about information about putting the object together here because shape mattered and the diamond shape matters. And a matter of fact, if you use certain shaped diamonds, you can't see them as coherent. And you use other shaped diamonds, you do see them as coherent. And so what this shows is, yes, there is a ventral pathway input into this that actually is involved in perceived object motion because knowing something about what the object is does help you figure out what direction it's moving in.
Do you see this system using object-based coordinate frames, extrinsic and extrinsic coordinate frames, or is it all internal? What do you think?
Well, the only evidence I have is the movie that I showed you about the oblique effect. Clearly, the initial coordinate frame that the information coming from the sensor is in sensor coordinates. So the initial oblique effect is in retinal coordinates, for sure. But then as you saw, over 400 milliseconds, it starts to tilt over to world. So my guess is that this signal that comes out here that's driving your motor control is actually a signal about what the object is doing in the world. But obviously, a lot more needs to be done to prove that.
So a question about the centrifuge study. So you went from 1G to about 4Gs. And could you go out on a limb a little bit and speculate as to the effects that you found? What sort of tasks would you expect problems with at 4G and maybe the size of those effects?
Well, what you would expect from the scrunching of space that we saw from the 4G, there's about, I'd say, a 10% scrunching. Maybe it gets worse at 5G. And during return, especially ballistic returns on Soyuz and other things, they can get up to 9Gs. You might expect that the world is getting scrunched vertically more. And it's not really a spatial scrunching, it's a directional scrunching. So what you might think is that, vertical tasks might be impaired, tasks that involve some vertical deviation. But once again, this is a motion stimulus that we showed there. So it would be hard to imagine exactly what motion control task you might have. But if you're actually trying to do some kind of manual control task, you might have a diminished gain vertically or an exaggerated gain vertically to compensate for this. And so you asked me to get out on a limb. We don't have any solid evidence for that, but obviously something is happening and more needs to be done to understand what's happening, but you might expect an asymmetry between behaviors that require information along the vertical axis as opposed to along the horizontal axis.
So please join me in thanking Dr. Stone for a great seminar.